Welcome to Wood Science. Impregnation of phytic acid into the delignified wood to realize excellent flame retardant. Introduction. Wood is a natural and sustainable material commonly used in building construction. Despite its advantages, wood is flammable, posing safety concerns. Flame retardant treatment is crucial for wood products used in buildings. Historical approaches. Fire-resistant coatings were initially used but proved ineffective over time, especially outdoors. Introducing flame retardant into wood fibers using biominerals. Phenol formaldehyde, PF, furfuryl alcohol, Fa, boric acid, carbon nanomaterials, and bentonite showed promising results, but faced challenges with toxic gas release. Intumescent flame retardant mechanism. A combination of acid source, gas source, and carbon source is key to successful flame retardant treatment. Wood serves as a natural carbon source, while introducing an acid source into the cellulose lumens enhances flame retardant properties. Phytic acid, PA, as a biosafe flame retardant. Phytic acid is a naturally occurring phosphorus-rich compound found in plants and is effective as a flame retardant in polymers. Modifying phytic acid and combining it with other additives is a promising research area for biosafe flame retardant solutions. Phytic acid was impregnated into the wood in this study. To enhance the impregnation of phytic acid, the wood underwent partial delignification beforehand. The flame retardancy of the treated wood sample was assessed through various tests, including the limiting oxygen index, LOI, vertical burning test, and cone calorimeter. Additionally, thermogravimetric analysis infrared spectroscopy, TGA-FTR, was employed to investigate the flame retardant mechanism. Following these processes, the wood samples were hot-pressed. The resulting wood samples exhibited excellent mechanical properties. Experimental materials. Chinese firwood specimens were chosen. Phytic acid, 70% water solution, supplied by Macklin Biochemical Technology Company loaded. Sodium chlorite, NaClO2, purity greater than or equal to 80%, provided by Macklin Biochemical Technology Co. Lieutenant. Acetic acid, AR grade, obtained from Beijing chemical plant. Deionized DI water self-made. Preparation of flame retardant wood laminate. Dilig wood with PA sample process shown in Fig. 1. Natural wood partly dignified, immersing a material in a solution containing 4% of sodium chloride along with acetic acid with a pH of 4.6. This immersion occurs at a temperature of 85 degrees Celsius for 6 hours. After rinsing with deionized water and ethanol, residual chemicals removed. Obtained wood dried to constant weight, recorded as Dilig wood. Dilig wood sample immersed in polyamide solution, 2%, 3%, and 4%, under 0.1 megapascal for 2 hours at ambient temperature. Subsequently, sample dried at 40 degrees Celsius for at least 6 AH until constant weight. Obtained samples labeled as Dilig wood with phytic acid N, where N represents the concentration of phytic acid solution. Wood sample without delignification also immersed in 4% phytic acid solution, labeled as natural wood with phytic acid 4. Characterization methods. Hermogravimetry analysis, TGA, measured using TA instrument Q50 thermal analyzer. Temperature range, 30 to 800 degrees Celsius. Atmosphere nitrogen. Heating rate, 10 degrees Celsius per minute. Sample mass, approximately 4 milligrams. Fourier transform infrared, FTIR. Instrument Nicolay Nexus 670. Wave number range, 4,500 centimeters to the power -1. Resolution, 4 centimeters to the power -1. Averaging scans 32. Some samples equipped with attenuated total reflectance, ATR device. ATR resolution 4. ATR averaging scans 128. Scanning electron microscopy, SEM. Instrument Hitachi S4800. Operating current 10 microamps. Voltage 20 kilovolts. Limiting oxygen index, LOI test. Instrument JF3 oxygen index apparatus. Sample size, 80 x 10 x 5 mm cubed. Standard ASTM D286317. Vertical burning test. Instrument CZF3 instrument. Sample size, 80 x 10 x 5 mm cubed. Standard ASTM D380119. Used to estimate UL94 standard. X-ray photoelectron spectroscopy, XPS. Instrument Escalab 250. Excitation radiation, aluminum K alpha Al Ka, 1486.6 electron volts EV. C1 spectra shifted to 284.5 electron volts. Fitted using XPS Peak software. Tensile and bending properties. Instrument Electronic Universal Testing Machine, E44104 Mester Industrial Systems Co. Ltd., China. Sample dimensions, approximately 100 x 6 x 1.5 mm cubed. Compressed along the thickness direction at a speed of 1 mm per minute. Thermogravimetric infrared spectrometry, TGA-F tier. Instrument DT50. Sample mass approximately 10.0 milligrams. Temperature range 25 to 800 degrees Celsius. Heating rate 20 degrees Celsius per minute. Atmosphere nitrogen. Flow rate 60 milliliters per minute. Results and discussions. Morphology of wood samples. Morphologies displayed in Fig. 2 for natural wood and treated samples. Little change in color and thickness after delignification and phytic acid permeation Fig. 2AC. Micromorphologies observed under SEM along longitudinal and cross-sections. Natural vessels visible under SEM, Fig 2A. Lumen structure maintained after delignification. Some areas hollow, Figner 2B. Coarsening observed after immersion with phytic acid, Fig 2C. Cross-section morphological change after delignification. Thinner cell walls, phytic acid crystal particles on wood vessel walls. Elemental mapping showed even distribution of phosphorus on the inner surface, Fig 2D. FTIR spectra comparison, Fig 2E revealed. Peaks at 28-48 centimeters to the power -1 and 14-15 centimeters to the power -1 attenuated after delignification. Assigned to CH2 and OCH3 groups in lignin. Dilig wood phytic acid, 4PA4 sample exhibited highest intensity in wide bands, 900-1200 centimeters to the power -1, attributed to PO and PO from PA presence. Burning behavior evaluation. LOI, vertical burning test, and cone calorimetry conducted for wood sample combustion properties. LOI and UL94 test results summarized in Table 1. Natural wood LOI 22.3%, burned out in 75s, no UL94 rating. Delignification treatment, LOI 20.3%. Burning time 31s, no UL94 rating. Immersion in PA solution, LOI 29.8% to 37.2%. PA weight gain increased. Achieved V2, V1, and V0 UL94 grades. Delignification and phytic acid substitution found effective for enhancing fire-resistant properties. Vertical burning test, Fig 3. Dilig wood with PA4 achieved VO grade in UL94 test. Cone calorimeter test implemented to evaluate real combustion flammability. Cone calorimeter test results, Fig 4 Table 2. HRR and THR curves displayed, Fig 4A. Natural wood, ignition at 23 seconds, 2 peaks in HRR 189.3 and 204K kWm2. Dilig wood with PA4, reduced PHRR 155.1 and 96.4 kWm2. TAR 14.2 MJM2, 71.4% decrease. TTI prolonged to 29 seconds. Dilig wood with PA4 left 34.3% residue compared to natural wood's 12.9%. Flame at 250 seconds, P2HRR for natural wood more vigorous than dilig wood with PA4. Treated sample exhibited better flame retardancy than the natural sample. SEM observation, Figure 4A. Char of natural wood collapsed. Basic cellular structure retained. Dilig wood with PA4 showed strong char, acting as good shielding for the substrate. Thermal stability. Evaluated wood samples thermal stability via TGA and nitrogen atmosphere. TGA and DTG curves compared, Fig 5. Key data in Table 3. Natural wood. Pyrolysis at 250 to 450 degrees Celsius. Tmax at 400.6 degrees Celsius, 18.4% residue at 800 degrees Celsius. Delignification. Tmax at 381.4 degrees Celsius. Residue reduced to 10.4%. PA substitution. Degradation at 150 to 350 degrees Celsius. Tmax at 264.1 degrees Celsius. Increased residue to 42.9%. Flame retardant mechanism exploration. Characterization of char FTIR and XPS, Fig 6. FTIR of dilig wood with PA4 showed differences. Peak at 1490 centimeters to power -1 cc double bond group. Peaks at 980 and 1100 centimeters to power -1. POC, aliphatic C and C in benzene ring. XPS survey spectra indicated P existence in dilig wood with PA4. C1's fitting, natural wood. CC single bond, co-single bond, OCO single and double bond. Dilig wood with PA4 CC single bond, CO single bond, OCO single bond and double bond. CC double bond. Ratio of CC double bond to CO double bond in dilig wood with PA4 indicated higher thermal oxidation resistance. P2P peak at 134.6 eV indicated POP single bond, showing PA cross-linked with wood carbon. Pyrolysis products analysis, TGA-FTR, Fig 7. TGA-FTR analyzed gaseous phase pyrolysis products. Natural wood peaks at 18 minutes, 385 degrees Celsius. Delig wood with PA4 peaks at 14 min, 305 degrees Celsius. FTIR spectra at 14 minutes, water vapor, CH2 or CH3 CO2CO. At Delig wood PA4 Tmax, highest CO production observed. Appearance of new peak at 970 centimeters to power -1 in Delig wood with PA4 indicated PO single bond band, signifying PA decomposition. Proposed mechanism. PA hindered wood decomposition, preserving more substrates. Flame retardant mechanism, Fig. 8. Proposed mechanism of PA on improving the fire resistance of Delig wood. Free radicals like popyrolized from PA captured free radicals, HHO. Pyrolyzed products from wood and PA cross-linked, leaving more residue with COP single bond and CC double bond, suppressing combustion. Mechanical properties of modified wood laminate. Longitudinal tensile strength of Delig wood with PA4 slightly decreased to 22 megapascals, but elongation increased to 2.6%. After hot pressing, tensile strength increased 6 times to 138 megapascals, and elongation at break maintained at 2.3%. Bending strength of Delig wood with PA4 increased to 50 MPa with a displacement of 2.7 millimeters. After hot pressing, bending strength of Delig wood with PA4 laminate reached 213 megapascals, 7.8 times higher than natural wood. Delignification and PA introduction didn't significantly change tensile and bending strength, but increased tensile strain and bending displacement. Comprehensive mechanical properties were sharply enhanced after hot pressing, attributed to H bonding between PA and cellulose molecules, Fig 9c. Conclusion. Novel flame retardant strategy implemented for wood sample. Delignification followed by immersion into 4% PA solution resulted in excellent flame retardancy, LOI 37.2%, decreased heat release rate, increased total heat release, and denser char for substrate protection. Hot pressing further enhanced mechanical properties, providing a feasible way for flame retardant wood-based building materials with high strength. Thanks for watching.